Alright, so what we're going to do here is we're going to look at non-circular motion to lay out the vectors that we're going to see when something slows up or speeds down in its rotation on a circle. So again, we have the radius component, and we have an object that's moving at varying speeds. Oops, that is not the brush I wanted to use. So, there we go. The brush tool cannot paint onto this layer. Now it can. I somehow added another layer. Let's get there. We go. That's better. That's better. My apologies. So here we have some force that's tangential and some force that is radial, generating an acceleration. Well, what that means is that they're no longer perpendicular to each other. And so if I look at this component, well, these two are perpendicular to each other, but the force itself is not perpendicular to the object. There's some net force here. And so I'm looking at the cosine component of it is radial, and the sine component of it is tangential. And so this object has a turning component, something to turn it, and also something to speed it up. And the component that is parallel to the radius is involved in turning, and the component that's perpendicular to the radius is involved in the speed that it makes on the circular path. So this is non-uniform circular motion. And what we're going to build is we've built the vector component of theta to be the equivalent of position. And so theta is an angle that you move around the circle. And so you can move an arc length, its linear component, arc length, or what we measured as x, is equal to r times theta. Take my radius and I move some distance, I'll travel a distance. My thetas per unit of time we're going to call omega, which is our angular velocity or angular frequency. How often we go around once is frequency, or it's the speed of the angles, the angle distance in radians we're doing per second, which we call velocity in our linear world. And so r times omega gives us the linear velocity, which is the velocity component in this direction. Now, when I have an unequal motion like this, well, when I have circular motion, I will always keep a tangential velocity, and the turning and speeding up and down can give me an inward velocity and an outward velocity. But if I hold my radius fixed, this body holds the radius fixed, and I'm not moving inwards or spiraling inwards, and I stay on the outside of the circle, this is the only thing I can have, is v on that tangential component. And so my accelerations, I go faster on the outside. And going faster, we're going to call angular acceleration, which we've been representing by alpha. And alpha is r times the acceleration component that we have. And we can do, and our acceleration component here is the thing that we want to look at, because this acceleration component has two parts. Alright, if there's a forces, I'm going to, whoops, jiggle you around there, sorry. I'm going to have an A tangential, and I'm going to have an A radial. The vector itself because these are at right angles, right? So I'm going to have an A radial and an A tangential. Because the vectors themselves are at right angles and the true A component will have a magnitude of A tangential squared plus A radial squared. And we can look at the angle you make to the radius to determine what the radial and tangential components are. And in angular vectors, we can actually write this as A has an r hat component, how much it's changing in the r direction, plus a theta hat component, how much it's accelerating. And if we hold the r hat fixed, the alpha r hat fixed, then the vector is just the theta component. And so one of the things we'll work on is translating tangential into theta hats, or tangential and radial into theta hats. All right. And so we want to introduce that it has two components. We can look at the magnitude of the acceleration. Now notice this is an acceleration vector linearly. It's linear. It has a angle that we can measure versus r, but it is a vector in xy components. And we're going to learn to translate that vector into r hat and theta hat components as we move through. And so that's what happens with non-uniform circular motion. We will do a lot of work where we hold r fixed. We have some solid arm that holds the particle. And so if it speeds up on a circle. But there are motions where I can speed up and the radius could detract and I spiral inwards. Right? So we can have a radius that changes also. But for right now, we're going to hold everything onto a circle.